In this video, we are going to study the Born-Haber cycle. We're going to study how we can be able to set up the Born-Haber cycle for a particular ionic compound. So we are going to be studying for aluminium chloride and magnesium oxide. What is the Born-Haber cycle? So the Born-Haber cycle is an energy cycle that uses Hiss's law in order to determine lattice energy of an ionic compound that cannot easily be determined in the laboratory. So we are concerned with using Hiss's law as well in order to find an expression from which we can calculate lattice energy. So there are different steps that an ionic crystal will undergo in the Born-Haber cycle, which we are going to elaborate. So let us start with aluminium chloride. For aluminium chloride to be formed, we need to have aluminium plus chlorine. So aluminium reacting with chlorine, we're going to have the formation of aluminium chloride. And to balance the equation, we'll put 3 on 2, making sure that the coefficient of aluminium chloride remains 1. For enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its constituent element. We must restrict ourselves to 1 mole, and the mole is formed from its constituent element on the standard conditions of 298 Kelvin and 1 atmosphere. So aluminium is solid, so it can be turned to gas by atomization. When we atomize aluminium, we're going to obtain aluminium gas plus chlorine. And after that, we can also atomize chlorine. Now, enthalpy of atomization is the heat absorbed when 1 mole of a gaseous atom is formed from its constituent element under standard conditions of 298 Kelvin and 1 atmosphere. So, we say we can also atomize chlorine. And to do that, we're going to have a gas with 3 different chlorine atoms. This is atomization of chlorine. Now, aluminium is in group 3, which means it has 3 valence electrons, and it can undergo 3 successive ionization energies. So when the first electron is lost from aluminium, it forms a plus aluminium, plus the electron removed, plus 3 chlorine gas. The second is removed, we have aluminium now with 2 plus 2 electrons plus the chlorine, and then the last electron is removed from aluminium. We have aluminium 3 plus 3 electrons now plus 3 chlorine gas. From here it undergoes 3 successive ionization energies. So I'm numbering of the enthalpy changes which we are going to use to find our expression. This is delta H4, delta H5, delta H6. So now from here we are going to electron affinity. So for ionization energy, we have, this is IE1, this is IE2, this is IE3. So from here we are moving now to electron affinity. Electron affinity now is the heat change when a gaseous atom receives an electron to form a negative gaseous ion. So chlorine requires 1 electron to have an octet, so chlorine is electronegative, so you can receive an electron, and in that we have to go chlorine, so we have EA1. Now we realize that there are 3 successive electrons that were removed, and there are also 3 different chlorine atoms, which means that each chlorine atom is going to receive 1 electron. So we are going to have aluminium 3 plus 3 chlorine minus. This is gas, this is gas. The states are very important. So we have these 2 gaseous ions formed. So each chlorine atom here receives an electron each, since there are 3 electrons that were removed from aluminium. Now when the 2 ions combine, the energy evolved is called lattice energy. These 2 ions will always combine to give back the same product we had, which is aluminium chloride. So this one is lattice energy. So now we have successfully drawn the Born-Haber cycle for aluminum chloride. How can we give an expression for this particular cycle using Hess's law? So we are going to use Hess's law and say roots. As I move, I can choose a clockwise direction. I say sum of the roots will equal the sum of anti-root. So as I move, wherever I move towards an arrow, it is a root. If I move against an arrow, it is an anti-root. So it means that, so I could call this delta H7 and delta H8. Okay, so we have this. So it shows that the only arrow I am moving against is this arrow for enthalpy of formation, delta H1, which means that delta H1 would just be equal to delta H2 plus delta H3 plus delta H4 plus delta H5 plus delta H6 plus delta H7 plus delta H8. So from here, any particular enthalpy can be obtained from the cycle. So if we are looking for lattice energy, our delta H8 is lattice energy. So we're going to make it subject of the formula here, and that will be all. And as a reminder, the coefficients on the chlorine where necessary also matter. Where we have here enthalpy of atomization of chlorine, there are 3 different atoms. So we've got to also consider the 3, which is coefficient, so that this is delta H3. We are going to multiply it by 3. And if we look at electron affinity of chlorine, which is delta H7, we are also going to have times 3, considering the coefficient. And that will be all for the Born-Haber cycle of aluminum chloride. Now let's go to magnesium oxide. For magnesium oxide, we have magnesium solid plus oxygen gas to give us magnesium oxide. So this is enthalpy of formation of magnesium oxide from its constituent element. The second step, we atomize magnesium. We have magnesium gas, oxygen gas. And next, so to balance here, to put half so that it becomes balanced. Here we put half. So we atomize oxygen. We have magnesium gas plus oxygen gas. Then we have to ionize magnesium to form an ion. Our magnesium will be able to undergo 2 successive ionization energies. We have this oxygen gas. The second ionization energy, we have magnesium 2 plus 2 electrons plus oxygen gas. And then our next step now is to go to electron affinity of oxygen. Oxygen is in group 6, so we undergo 2 successive electron affinities, which means that we are going to come to first electron affinity EA1, where we'll have magnesium 2 plus 1 ion or 1 electron that is left plus oxide, which is minus after oxygen has received the first electron. And then oxygen will then receive the second electron, and the enthalpy change now will be opposite. We will have EA2 and we have magnesium gas ion plus oxide 2 minus, and when these 2 combine, they will come back to give our ionic compound, magnesium oxide. So we realize that the second electron affinity is upward and the first is downward. So for all the arrows pointing upward, it shows that the reaction is endothermic, and for those pointing downward, it shows that the reaction is exothermic. To that effect, second electron affinity of oxygen is endothermic because we are adding the second electron to an already existing negative ion. So there is some sort of repulsion between the negatively charged ion and the second incoming negatively charged electron, and so work must be done in order to overcome the repulsion. That is why it is endothermic. So having drawn this, let's label the enthalpy changes as well. We have here H1, which is formation. We have H2, which is atomization of magnesium. We have here H3, which is atomization of oxygen. We have here H4, which is first ionization energy, second ionization energy, H5, and then we have H6, which is first electron affinity. We have H7 and we have H8. So these are the different enthalpies we have. If I take a clockwise direction, so I am moving against this arrow for second electron affinity, and I'm also moving against this arrow for enthalpy of formation. So I'm going to say sum of root will equal sum of anti-root. So delta H1 plus delta H7 will now be equal to delta H2 plus delta H3 plus delta H4 plus delta H5 plus delta H6 plus delta H8. So if we are looking for lattice energy, which is delta H8, we can always make this subject of formula, and we will calculate our value for lattice energy. So that is it for this video. If you found it helpful, give it a thumbs up. Thanks for watching.